Welcome to day one. We will need our calculator in today's video, so if you could have that out. For the couple people that don't have their packets yet, it is on Schoology in the class materials folder under Unit 7. If you wanted to print out the couple pages or just do it right in your notebooks is fine as well. So our new unit is a really long unit. It's 25 days. It's on series and sequences. It tends to be the most challenging unit in AP Calc BC. With that being said, students at our school tend to do 3 times the average on the AP exam with this topic. So nationally it is the hardest topic, but students at our school tend to do 3 times better. And part of the reason for that is we go pretty quickly, and you started calculus last year with Mr. Delands, so that we have a 25-day chunk of time to be able to do series and sequences. So we stretch it out probably a little longer than other schools to just give you a little bit more time to be able to digest things each day. So we're going to be in our notes packet on the day one stuff. So a sequence is a list of numbers. It's a function whose domain is discrete. You saw sequences maybe a little in Algebra 1, but you definitely saw them in Algebra 2. A common way to notate them is with a letter and then a subscript of n. So we have there a sub n, where a sub 1 is the first term, a sub 2 is the second term, and so on. If we're talking about some general term, we refer to it just as a sub n, the nth term, some term down the line. So in these examples, we're going to find the first 5 terms. Well, if we want to find a1, 1 is now in the n spot, so we just sub 1 in for all the n's. So we're going to have 1 over 2 times 1 plus 1. So that's going to give us 1/3. For A2, we'll fill in 2 for all the n's. So that's going to be 2 over 4 plus 1. So we'll have 2/5. For A3, we'll put in 3 for all the n's. So we're going to have 3 on top. 2 times 3 is 6, plus 1 is 7. And if we keep going, 4 in the numerator, 2 times 4 plus 1 is 8. 2 times 4 is 8, plus 1 is 9. And then we'll have 5 over 11. So those would be the first 5 terms in our sequence. Going to the other one, for A1, let's think about the negative first. When you put 1 in the exponent for that -1, it's going to come back negative. When you put in 2, it will come back positive. When you put in 3, it will come back negative. So essentially, all of our odd terms should be negative, and our even terms should be positive. So if we put the 1 in the fraction, we'll have 1 squared, which is 1. 1 plus 5 is 6, so we'll have 1/6, but then the negative, because it was an odd power, so -1/6. For A2, we know this one will be positive because the negative is raised to an even. 2 squared is 4, 2 plus 5 is 7, so we get positive 4/7. A3, we're going to have a negative, and we'll have 9/8. A4, we'll have a positive, and we'll have 16/9. And for the 5th term, A5, we'll have a negative because of odd power, and 25/10. And you could reduce that if you wanted. Sometimes with sequences, you don't necessarily see them reduced always, just because it helps you figure out the patterns better. But there will be occasions now and then where they will be reduced, but sometimes you don't see them reduced, just easier to pick out the patterns. So example 2 is what's called an alternating sequence. That's because it alternates signs. So you'll recognize an alternating sequence most frequently by that -1 raised to a power. But there are ways to get an alternating sequence using writing cosine or sine in certain ways as well. So this is the most common way to see an alternating, but other occurrences might happen as well. So how can you do a sequence on the graphing calculator? Well, there's a couple of ways. So we're going to go over to your calculator, and the first place we're going to do is a calculator page. On the calculator page, we're going to type in SEQ for sequence. And we used that when we did Riemann sums. And then there's 5 things that we have to put in the sequence. First, we want to put what was the formula, and we have to put it in with x's as opposed to n's. So we're down on the bottom there where it says on calculator page if you want to follow along on your notes packet. So make sure you're out of the fraction, and then we'll do a comma. Next, you have to tell what the independent variable is, which is just x. Then we tell it what is the first value then we want to sub in, comma, what is the last. So we want to go from 1 to 5. And then the last thing is you tell it what's the step size. So for our sequences, we'll always be stepping by 1 because we want to do integers. Now the last thing you have to do is the calculator is defaulted to give you back decimals with this. So if you go menu, number, and approximate to fraction, that'll make sure that it gives us fractions back. So if you hit enter, that gives you each of our values, and those are our first 5 things there. So notice this is really nice, especially if you had to do a whole bunch of terms. It would be a pain to punch them all in. So if say you had to do 20 terms, you can get the first 20 terms of the sequence pretty easily. What I would like you to do, let's see if this works. I'm not 100% sure this will work. Highlight that and do Control C for copy. Then we're going to add a list and spreadsheet page. So do Control Doc, and go down to list and spreadsheet. And we'll see if we can paste this in the formula spot. So in the equal spot, then do Control V. Oh yes, it worked. So you paste in the formula. Now, if we hadn't already had that, we would have had to type in the exact same thing we did on the calculator page. And notice it just gives you it now in a list and spreadsheet. So that's how you can do it on a list and spreadsheet page. So now on a graphs page, let's do Control Doc, and we'll go to a graphs page. We need to switch our mode. So we have to go to Menu, Graph Entry, Edit, and we've got to go down to Sequence Mode. Notice our variable in the parentheses here is n. So this time when we put it in, we're going to put it in terms of n's. So we'll do the same sequence, but we'll have n over 2n plus 1. Leave your initial term blank because we didn't define it as a recursive formula. And if you enter, those are all our terms. Now, a couple things we can do. If we do menu, trace, and graph trace, it's going to give us each of the values. So this is telling us when n is 1, we get 0.3333 back. There we get 0.4, and if you just keep hitting the right arrow, it'll give you each of the values. Now the downside is that's in decimal form. So the other thing we can do is if we do a Control T, it'll give us those same values in our table. So again, downside decimal form, but what we'll want to do in a lot of cases is see if our terms are converging or diverging. So therefore, the decimal form will still allow us to see if it's converging or diverging. We can look a ways down, scroll down a bit and see, oh yeah, this is getting pretty close to a half, it looks like. So that's a quick way to be able to do that. So if we go back over to the notes packet, we're going to go to page 2. So as I mentioned, the main thing we want to know is if things converge or diverge in this course with our sequences. That first one is just the example we saw that converges to 1/2. And we're going to do this on the bottom, but if you think about it with a limit, as n approaches infinity, you would get infinity over infinity here, and then when you take the derivative, you would get 1/2. So doing L'Hopital's rule could help you out with that. Now the next one, there's the picture of the graph. We can really think of that as being the same as saying 1/3 to the n, because 1 to any power is going to come back as 1, and now that looks like exponential decay. And then it makes sense. Okay, yeah, that's going to go to 0. The other way you can think of it is if you think of it as a limit, as the numerator stays as 1 and the denominator gets huge, that's going to get closer and closer to 0. If we look at the bottom one, though, notice it's just bouncing back between -1 and 1 with a stop at 0 in between. So there's no limiting value. If it doesn't have a limiting value, we just say it diverges. In this unit, if you have a sequence or a series problem, which we'll eventually see, and you are stuck, one of the best things you can do is write out the first 4 or 5 terms, just so you can get a sense of what's happening with the sequence. So if you're ever stuck, write out some terms, and that can help you wrap your head around what's going on. All right, so something we know, our limit as n goes to infinity. So if our terms go to infinity, can be determined by letting x go to infinity and just putting it in with an x. By doing it as an x, then it fits L'Hopital's rule. That's the main reason for switching it to x's. So what we're going to do for this first one, we'll just do limit as x approaches infinity. And we'll write this as 4x minus 7 over 3x plus 2. Well, these are both going to be huge as x becomes huge, so we can do our L'Hopital's rule. And this will become 4/3. It's a constant, so it'll always be 4/3. So this will just approach 4/3 as your number of terms becomes huge. If you remember back to graphing rational functions, that's like we're finding the horizontal asymptote as well. So when the degrees are the same in polynomial things, you just take the ratio of the leading coefficients. So that's also a quick way of how you can get to 4/3. So if we do the same idea in the next one, so we're going to get huge things on top, huge things on bottom, so we can do L'Hopital's. So we'll get 2x. And the bottom, we get to review something from earlier in the year. What's the derivative of an exponential? That's a to the x. Well, our derivative rule was a to the x times ln of a. So in our denominator, we're going to have 2 to the x times natural log of 2. Well, this is still an infinity over infinity. So I'm going to go over here now. So we'll do it again. 2 to the x's derivative is 2. Natural log of 2 is just a constant, so we can ignore it for a second. 2 to the x's derivative is 2 to the x natural log of 2, and then bring that natural log of 2 constant back in. Well, now as x goes to infinity, the bottom is going to get huge. The top is going to approach 2, so 2 over a million, 2 over a billion, 2 over a trillion, that's going to approach 0. And that's the idea that an exponential is going to grow quicker than a quadratic. So for this next one, we'll have limit as x approaches infinity. We'll have 5 plus -1 to the x. So this one is not rational, so it doesn't meet L'Hopital's standards. So this would be one where let's just write out a couple terms if we're unsure. So if we subbed in 1, we'd get back 4, because we'd have 5 minus 1. If we subbed in 2, we now have a positive 1, so we get 6. If we sub in 3, we have a -1, so we're back to 4. So 4, 6. So by writing out a couple terms, hopefully we see, okay, that's just bouncing between 4 and 6. That's not going to approach some value. So this one diverges. And the last one, if we do our limit as x approaches infinity, cos pi x. Well, cos, even when the frequency is changed, it's still just going to stay between -1 and 1. So this is going to diverge because it does not approach a value. So knowing what our common functions do and how they behave will help us out a lot in this unit to determine if they're going to approach something. All right, on to our last page in the notes for this video. So does -1 raised to the n converge? Well, if you're not sure, write out a couple terms. When we sub in 1, we get -1. When we sub in 2, we get 1. When we sub in 3, we get -1, and so on. It's just going to alternate. So none alternates. Okay, so that does not converge to some value. Now, just because you have a -1 to the end, if you had other stuff in the sequence, sometimes it might converge. So for example, graphically, you might have something that's going like this and it's approaching 0 but bouncing back and forth from it. So it will eventually approach 0, it's just bouncing back and forth on either side of it. So sometimes even if you have a -1 to the end, it might still end up working out. All right, so we're going to look at 3 cases with s and t here. S and t is some fraction. So first we're going to imagine that s is smaller than t. So we're going to do the limit as x approaches infinity of s over t raised to the x. Well, just to wrap our heads around it, let's pick a number where s is smaller than t. Let's say we had like 1/2 to the x. Well, that would represent exponential decay, so that's going to get smaller and smaller and smaller, so that will approach 0. Next, let's look at the case when s is bigger than t. So we'll again do our limit as x approaches infinity of s over t to the x. So just so you can think about a case, think about if you had 3/2 raised to the x. Well, that's going to be exponential growth, so it's going to get larger and larger and larger. So this one diverges. And if s is equal to t, so we'll again do limit as x approaches infinity of s over t to the x. To give you an example, let's say we had 3/3 to the x, which is like saying 1 to the x. Well, first term is going to be 1, second term is going to be 1, third term is going to be 1, and so on. So this is always going to be 1. And our last slide for today, let's see if this converges to something. So we want to do the limit as x approaches infinity of 1 plus 1 over x, all raised to the x. So as x goes to infinity, 1 over x is going to get tiny. So this will be like a 1 in the denominator, or in the base, I should say. And the exponent is going to get huge, so that's 1 to the infinity. Our 3 indeterminate forms for exponentials were 1 to the infinity, 0 to the 0, and infinity to the 0. So this is one of our cases that we saw on day 8.5 in last unit. So our technique was we could rewrite this as limit as x approaches infinity. We could write it as e to the natural log of what we had, because e to the natural log of your stuff is still just your stuff, just written in a different way. And then what we would do is we would do our limit just with the natural log stuff, because that's where all the x's are. And we would just remember in the end that we've got to do it as e raised to something. So the purpose of doing this is it allows us to bring our exponent out front. So we'll have limit as x approaches infinity. We'll have x times natural log of 1 plus 1 over x. Well, the x goes to infinity. 1 over x goes to 0, so we're approaching natural log of 1, which is 0. And infinity times a 0 is an indeterminate product, so we need to move one of them to the bottom. So it's tougher to move natural logs to the bottom, so we're going to move the x to the bottom as 1 over x. So we'll have natural log of 1 plus 1 over x In the denominator now we have 1 over x. So this is still 0, and 1 over x, as x goes to infinity, will get really small, so that's now over 0 as well. This will allow us to do L'Hopital's. Natural log's derivative is derivative of the inside over the inside. So our derivative of the inside, derivative of 1 is 0. 1 over x, think of it as x to the negative 1. So its derivative is negative 1x to the negative 2, or in other words, negative 1 over x squared. So we'll have a negative 1 over x squared over the original inside of 1 plus 1 over x, and then over the derivative of 1 over x, which we just saw to the left was negative 1 over x squared. Well, if we think of this as a keep change flip, we have negative 1 over x squared over 1 plus 1 over x, and then times the reciprocal of our denominator, so it'll be negative x squared over 1. So these multiply together on top. A negative times a negative is a positive, and x squared times 1 over x squared is just 1. So we're going to have limit as x approaches infinity. We'll just have 1 in the numerator. And on bottom, we'll have 1 times 1 plus 1 over x. Well, now as x goes to infinity, the 1 over x goes to 0, so this will just be 1 over 1, which is 1. Don't forget we had to do e raised to that, so we have e to the first, so really we just have e. So let's go back and look at the original. This just approached e. This was something we talked about briefly in probably December, I would say. What this is really saying, when x goes to infinity, we have 1 plus a tiny to a huge. 1 plus something approaching 0 to something approaching infinity, and we talked about how that's what e really is. That's how e can be written as a limit. That's it for this video. Have a great rest of your day, and we'll see you tomorrow.